Let's now continue from big O. So last time I went very quickly just about the mathematical foundation. For those of you who did not take 1019, it's okay. It's not really rocket science. It's very easy. Read over my slides. If you really got trouble of understanding, either rewatch the video or come to me for help. Okay, the mathematical part is not difficult. Okay, don't really find excuse for yourself. So now, well, from now on, we're going to draw a connection from big O to this course. So why do we learn big O? Because we would like to judge the quality of code. I'm going to give you some examples for now before we move to a new topic. Okay? These are simply just code that you should be familiar with already. Let's analyze their complexity by using big O, just quickly. Okay? So now I'm going to just use the iPad. I also got the duplicates over here. Okay. The first one, now let's have a look at here. The code here is simply means, does my array contain duplicates? So now first of all, let's understand what the inputs are. Okay, do I have my, okay, bear with me. Okay, I need to, okay, look at the code for now. I'm going to connect my Apple Pen. Look at the nested loop. Think about what that complexity should be. Should that be constant, linear, or should it be quadratic, etc. Okay, think about that. I'm going to reconnect. Okay, have some thoughts about that, and then I'm going to reconnect my iPad. Okay. Okay. QuickTime, and then File, Movie Creator, Recording, and then iPad Pro. Oh, come on. Okay, good. Okay, let's go back to iPad. Okay, now full screen mode. Okay, now, any idea the complexity about this? Okay, one answer. Quadratic, which is n to the power of 2. That's what you claim. Any other answer? So I would say from this course, we don't necessarily have to count the precise number of primitive operations anymore. We don't have to. However, you should have a good sense about how to justify your answer. Okay? So quadratic is correct, but how do you justify that? Okay? Typically, if you have a nested loop, what you really have to focus on is the body of the loop. Let's only focus on the body of the loop and figure out exactly how many iterations you would need. Okay? That's how we're going to do. Okay? Let's now analyze this. This one is quite typical. First of all, where is the body of the loop? So it is this part over here. Okay? It's basically this part. Okay? This is basically the body of the loop. And we'll worry about I and j in just a moment. Somehow I and j, they will control how many times this part of the loop is going to be executed. If you only look at this block alone, what will be the complexity? Just that one. O1 or On? Okay, let's have a look at this. We have some comparison here. We have some logical disjunction, some logical operation, some arithmetic, return, assignment, and plus. All of them are cheap, right? You can see that. So just for this part here, it's big O of 1. Okay, just for that part. Now, what we have to worry about is how many times exactly, in the worst case, this can be executed. That's what we got to worry about. You don't have to think about the best case, where you're going to return true maybe early on. You don't have to worry about that. We only worry about the worst case. So now, in this case over here, so now we know that, first of all, the body of the loop takes big O of 1. So now the question is, how many times are we going to execute it? How many times? Exactly. Okay? Let's now analyze the loop counter. You can see for I is going to start from 0 over here. That's going to be the starting value. And then, let's say for the very first iteration for the outer loop, I is going to be 0. What about j? J is going to be from 0 until n minus 1. Agree? For those n iterations, we're going to run the body of the loop. Okay? But this is only for I is assigned to 0 initially. Okay, so now you can see that over here we got n, okay, from 0 to n minus 1. So that's only when I is equal to 1. What about when we try to say I plus plus? So we're going to get I is incremented to 1. And now we start from j is assigned to 1 up to n minus 1. So how many do we have? N minus 1, right? You can see somehow if you keep going like this, let's talk about the very last iteration. So when I is equal to, let's say, n minus 1, in this case, j will be from, you can see that j is always, will start from 0 until j is less than n, right? That's how j is going to change. So now in this time, j is going to be from 0 until, oh, sorry, over here. Did I do something? Oh, I did kind of, it should be 0, right? Not really. Okay, I was talking about another example in later, so I got myself confused. What about we undo? Okay, that's the beauty about iPad. Okay, don't worry. What you just listen, I'm going to repeat it again for the next example, okay? Let me do it again. Sorry about that. Okay, first of all, let's see how when initially I is initialized to be 0, right? I is initialized to be 0. That's what we have. And what about j? Okay, let's do it again, but you get the idea. When I is equal to 0, j is going to be from 0 until n minus 1. So this one will be n. And then when I is incremented to 1, j is going to be also from 0 until n minus 1. So the value of j is not affected by I. Okay, it's completely dependent. So that's also n. Okay, so we keep going. So what's going to be the last iteration? So that's when I is equal to n minus 1. In that case, j is also going to be from 0 until n minus 1. So that's also n iterations. So how many iterations in total do we have? N times n, right? Okay, hopefully you see the pattern over here. I can tell you that in principle, for most of the cases for the loop, you just have to first of all analyze the body of the loop. If that happens to be constant or any other time, analyze that first, and then figure out, based on the loop counters, how many iterations you will get in total. That's exactly what I do, okay? So now, how many times of iteration you got? N squared. So now the running time is going to be big O of 1, and then times n squared. So you just get big O of n squared, okay? So that's the answer. Okay, that's for this loop here, quadratic, okay? So if I give you something like this in the test or in the exam, the satisfactory answer would be, first of all, tell me that it's big O of n squared, and then the way to justify, you can tell me the body of the loop is big O of 1. Just tell me it's all primitive operation, that'll be enough. And then you would say that now, based on I and j, I can see that it's going to be n times n, which is n squared iterations. And I'm going to n squared multiply big O of 1, which will be big O of n squared. Okay? That will be the answer. Okay, another one. This one over here is actually should not be surprising. I kind of combined the previous two examples together. Okay? Let's try to read it together. Somehow the name of the method doesn't really matter. We just want to analyze the code structure. Okay? So now let's try to see that. I will help you out to save time. First of all, you can see that this part here, just this line, how expensive is that? Should be constant, right? This one just constant, big O of 1. That one is easy. And then what about this loop over here from 3 to 5? Big O of n, right? We talked about this already, right? 7n minus 2, but it's big O of n. So this one over here, I'm going to write it here, big O of n. And what about line number 6? O1, thank you, big O of 1. And from 7 until 9, that's something we have just done. N, big O of n squared. And then we got the final one, return, big O of 1, okay? So what we have got, you can see somehow each step is completely independent, which means do one and then followed by the other one. They are not really nested. If they are nested, you got to multiply. If they are somehow independent, you can add them up. So what you will get is something like this. So the running time is going to be big O of n plus 1 plus n squared plus 1. As we said before, to determine, only keep the highest order. Drop the multiplicative constant and drop the lower terms. So what you will get is n squared. Okay? So this one, even though you got 2 loops over here, you got 3 loops actually, but only 2 are nested. The other one is completely independent. Okay, so you can see that we just want to introduce you one term. So we say that computationally speaking, line 7, 8, and 9. Okay, I'll try to use a better highlight. When you see the recording, you'll see the color. So 7, 8, and 9, we say that this particular stage dominates. It dominates the running time because that's the highest power, n squared. Okay, good. Okay, this one, I believe that's the last one. Let's do this one. Actually, this is the one that I was confused with myself with. So let me try to read it out to you. In line number 4, I say that integer j is initialized not to be 0, but I. That's why I was confused, okay? That's something I was supposed to do, okay? I meant to do. Okay, think about this. Do you think, now, intuitively, you can see that for line number 4, line number 3 is basically the same as before, but for line number 4, the initial value for j is actually not 0 anymore, it's actually I. It seems like we are running fewer iterations over here, but is it going to change anything though? Still quadratic, okay? Yes, exactly, okay? But I will demonstrate that to you, okay? Somehow you will see that it turns out to be an arithmetic sequence, okay? Yeah, I'll show it to you. Yeah. Okay, I'll read it. Okay, the blue, you cannot see that. I'm gonna write it here. J is initialized to be I. Yeah. Again, sorry about the projecting. I'm gonna complain to the school for sure tomorrow morning. First thing. Okay, now, let's try again to be systematic on our analysis. First of all, this is the body of the loop. Okay, this part here. And we know that this is big O of 1. Now the question is, how many iterations do we have? How many iterations? And if you want to figure out how many iterations there are, look at the loop counters. Okay, we got I and j. Okay, so now we got I, when I is assigned to be 0, it's at the very first iteration. In that case, j is going to be from I until n minus 1. In this case, j will be I, in this case, 0. 0 until n minus 1. So we have n iterations, agree? For the very first time. Now, when I is incremented by 1, so we got I is 1, and then we have j is starting from 1, not 0 anymore. Okay, so 1 until n minus 1. So we got n minus 1. We got 1 strictly smaller, right? If you keep this pattern going, when I is incremented to n minus 1, that's basically the last iteration. In this case, j will be from n minus 1 to n minus 1. So just 1. So how many iterations do we have? It's going to be n plus n minus 1 plus n minus 2 plus all the way to 1. That's a typical arithmetic sequence. So that would be, well, of course, you can say n times n plus 1 divided by 2. And we know that it's going to be, well, you don't have, well, if you n squared plus n divided by 2, but now we can drop all the lower terms. And this is simply going to be big O of n squared, because you can only keep the highest term. Okay, that's how you solve this problem here. I will try to give you something a little bit more challenging as an exercise for you. You can feel free to discuss as a group. I'll give something that's really challenging. How about that? Okay? And then we can discuss that when we have time. Any question about asymptotic analysis? And that's it. And we can move on to a new topic. Okay? Good. Okay, we're done with the slides. And now I would like to talk about linked list. Linked list is really a lot of fun. But before I talk about linked list, I'll spend about 10 minutes or so to give you a little bit background. Okay? Again, we need to know about the context before we talk about specifics. Okay, so I'm just going to introduce the idea about ADT, abstract data types. You'll learn much more again in 2011 and also 3311. 2030, we just briefly touch upon that. And we're going to go back to arrays. I'm going to give you some little bit challenging exercise to decide, again, big O. And then we'll move on to linked list. We may not finish everything today. Hopefully, I'll give you enough ideas so you can also try to do some self-study over the weekend. Okay, abstract data types. So what's really abstract data types? So whenever you're trying to solve a problem, the solution that you're devising is basically an abstract data type. Okay. For example, what you do today. I shouldn't say the lab test. Sorry, I'll save that for next week. Okay. So for example, what you did for the birthday book. Birthday book is an abstract data type. Why? Because it's application there. So what kind of operation does it support? You can add an entry, you can remove an entry, you can get a birthday of a name, you can also remind for a particular birthday. You got 4 different operations to support. Whenever you got some application there, it's like a black box, and then you got several operations you have to support for the clients. It's basically abstract data type. Okay? So you got many examples there. Okay, so now whenever you talk about abstract data type, you basically talk about this picture over here. So that's like a black box over here. So you have some interface. Interface simply means the public methods or attributes you allow any other user to call on your class. And what's really interesting is something that's hidden from the clients, data structures. In this course, we only talk about several very fundamental, very basic data structure. Linked list is the most important one. And the data structure you have learned so far is array. That's the only one you have learned. Okay? But we'll see that array is only one of the fundamental ones, but array doesn't really work that well usually. So that's why in the next slide, I'm gonna tell you under what circumstances you should not choose array. You should choose something else, which is linked list. Okay? You can read it through. It's just about some general concept. Okay? For you as a supplier, you have to make sure you choose the right data structure, either array or linked list, whichever that has a smaller big O. And also, you might want to make sure you got correct code for your clients, etc. Efficient performance. Okay. One more slide. And why do we develop ADT? ADT, again, another example would be all the library classes you have in Java. They are also ADT. Array list is an ADT. Hash table is an ADT. Tree map is also ADT. So they have already defined over there where you don't have to worry about how they are implemented. You can simply just use it. And they usually tell you what methods they actually support. For example, for array list, you can say add or get or index of, etc. Okay? So they're reusable components. Oh, okay. The one you cannot see here, that's a critical bit. That's called reusable components. Something that you don't have to reinvent. You can simply reuse. Okay. Okay, so for this course, we will talk about stacks and queues. So these are interesting data structure, but they're very easy. They're very useful. We're also going to talk about trees very briefly, binary tree. Okay. Okay. Every time we talk about ADT, you are expected to actually implement and design. Okay. So you're going to implement in Java, and also if I give you any new operation to support, you should also design certain algorithm for that. Okay. We'll get there. Okay. Okay. So now for the basic data structures, we got arrays and linked list. I'm just going to review array in one single slide very quickly, and then we'll go to the linked list. Okay. Now, I'm going to review the array not from the syntax point of view, but from the performance point of view. We want to know when we should use the array and when we should not use the array. In that case, we have to know what kind of operation will be very cheap for arrays, and what kind of operation will be very expensive for the array. Okay? When it is expensive, you should not use array. That's my point. Okay, let's see that for array. First of all, array, it has indices, and this is the important thing. Size of an array is fixed. When you declare an array, when you first create it, you have to declare the size to say assign new integer array of size maybe 100 or 30, right? So it's always fixed size. But what if your array is full? What should you do? How can you add new entry to the array? If you create a new array, what's going to happen? You have to create a new array of maybe size 200, from 100 to 200. And then you got to copy all the old contents into a new array. That part is expensive. Okay? So, that'll be enough intuition here. Okay, so what kind of operation do we have for array? Okay, let's just go over the basic one, which you already know. But now, let's say accessing If you say, I want to go to the first position or a particular position for the array, that one is very cheap. That's one of the primitive operation. That one is simply just big O of 1. That's constant. So if for, again, that's big O of 1. Okay? Whenever your application, you want to get access to a particular location frequently, you should really consider array. Okay? That's the efficient part for the array. Now, what about updating? If you want to assign to a particular position of the array, that's also very cheap, right? You want to get to a particular position and then assign a value to it. That's also cheap. Okay, that's also constant. Now, what about inserting and removing? Think about the birthday book exercise you did. If I want to remove an entry, one possible way to do it would be I want to shift everything to the left by 1 position, right? In that case, that's very expensive. Right? Because it might be that I want to shift all the way from the second position to the left, and third to the second, fourth to the third, and etc. Right? It's going to be very expensive. It's going to be a linear operation. Let's get some intuition over here. Okay? I'm going to show you the code on the iPad. Okay, so now let's read it together. Okay, and then I'll give you an example. Let's say over here, let me use a different color here. So now something called insert at. What it will do is, given an input array, let's say array of string, just make it simple. And what we are trying to do is, we are input array, and the size of the array is n. So we can analyze the performance of the array. And then we are trying to add a new element into the array at index I. Let's see how this works first before we see the code. If I say, let's say I got names array over here, names, that is pointing to an array of size, let's say 3. So index 0, 1, and 2. Let's say Alan, Mark, and Tom. We got 3 names over there. Okay. Now, if I do the following, I say names dot, I can say, okay, let me do it properly. Let me just grow that a little bit. How about that? Number 3, Jim, and then 4, Simon. An array of size 5. Now, if I say insert at, and then first of all, I put the names array inside as the first argument, and then the size is simply just 5 over here. And then I say also, let's say I want to insert, let's say, what about Jeremy? Jeremy into position, let's say 1. Let's say 2. Okay, this is how you can use the method. Okay, I'm trying to insert into the array. As you can see, we already occupy all the slots in the array. So the only way I can add a new slot into it is by resizing the array. Okay, let me show you how the output should look like, and then we can go over the code. Yeah. Oh, 5 there. Okay. So 5 there is basically the size of the array. It's a.length. Because over here you can see the names. We got 1, 2, 3, 4, 5. That's why I put 5 there. Okay. It's a little bit contrived. Okay. But the 2 there is more important. We're trying to insert into 2. Okay. Okay. What this will do is as follows. Okay. So now this is the input. Well, after this, what we should get is like this: names, and then we have a strictly longer array. So 0, 1, 2, 3, 4, and 5. You can see the input array, the size is simply 6, right? And what you should expect to see is, I should see Jeremy at index 2 for sure. Okay, that's what the problem is requiring. So I should get Alan, Mark, and Jeremy. What about Tom? Tom used to be at position 2, but Tom will be shifted to the right from 2 to 3. Tom, and then Jim, and then Simon. That's what I would get. Okay? Conceptually, that's easy. Let's look at the code very quickly, and then we'll analyze the complexity of the code. Okay? So now you can see that that's exactly what basically there are 3 stages for the code. Very easy. You can see that we are trying to insert into position 2. So anything before that should correspond to exactly the input array. So Alan and Mark which means they are indices before 2. They should be exactly copied over here. And then we assign to index 2, Jeremy. And then for the rest of the array, we simply copy from the old I position over there, Tom, Jim, and Simon. But we're going to shift them. So you're going to play around with the indices a little bit. Okay? Let's see how that can work. Okay? So that's exactly the 3 stages you will see in the code. So you will see that this is, so first of all, you can see this one over here. So this part over here, you can see we are trying to create a big array of size n+1. So this line here is not expensive, it's just creating an array. So this part here is big O of 1. That one is not expensive. Now we have a loop over here. Okay, that's the second stage. Okay, that first stage, I'll say first. And this is second stage, and this is the third stage. So 3 stages over here. The first stage, we say that J is going to be from 0 until I minus 1. Okay, and then we're simply going to say the result. Okay, let me call this result. How about that? Okay, the output array is going to be a position I is exactly equal to AI. Okay, so this is input. Let's call it A. Okay, just different name. So now I is actually 2, right? This is I. So I is over here. So this is just I. So we're going to go over the array from 0 until I minus 1. Okay? And then we're going to say result at I is assigned to AI. For example, result at 0 is assigned A0. In this case, we are copying over Alan into here. Okay? And then in the second iteration, result at 1 is assigned to A1. In that case, Mark is copied over here. Okay? So this is the first stage. Okay? This is what the first stage will do. Any question about the first stage? Any questions? So now, what would be the running time for the first stage? Worst case. Worst case. So first of all, let's be a little bit more mathematical. How many iterations do I run for line number, oh, I don't have line number, but for the first stage. How many iterations exactly? I minus 1. So how many iterations I have exactly depends on how large I is. In general, how large can I be? I can be maybe the last index in the array, right? In which case, I got to copy everything over in just the first loop. So in principle, I can just be the length minus 1. Okay? So now this part over here, second stage, depends on I. Depends on how large I minus 1 is. In this case, in the worst case, it can still be just big O of n. Okay? Already in the first stage, it's already going to be linear. Okay? Now, what about the second stage? I simply the result I is assigned to E. In this case, I is 2. So result 2 is assigned to Jeremy. So I simply put Jeremy here. Okay, this is the second stage. How expensive is second stage? Just 1, right? But in some way it doesn't matter anymore because that one is already shadowed by the previous one, right? It's already dominated. Okay, but we should still know big O of 1. Okay, now let's look at the third stage. In some way, the third stage is very similar to the first stage, very similar. So now I'll get to your question. Let's run through the code very quickly. So now it's going to be from I plus 1 and j less than, basically from I plus 1 until n minus 1, right? Okay, so now I'm going to write some explanation over here. For the third stage, j is going to be from I plus 1 until n minus 1. How many iterations do we have? Let's be mathematical. How many numbers do we have in between this? It's going to be n minus 1 minus I minus 1. I believe plus 1 as well, right? Just calculate how many numbers are in between the intervals. So we got n minus I, n minus 1. Okay, something like that. Okay, so now this is how many iterations? Number of iterations for the third stage. So now you can see that it's actually n minus I minus 1. Okay, let me just finish this before I get to your question. How about that? Okay, so now, what's the worst case for this number? Exactly. From the previous one, the number of iteration is simply just I minus 1. So the larger I is, the more expensive the first stage is. Now, in the third stage over here, the smaller the I is, the more iteration we will get in the third stage. Okay? So now in the worst case, when I is, the worst case is when I is simply equal to 0. In that case, we also get big O of n also for the third stage. Big O of n. But if you add them up together, it's going to be still linear. Okay? It's going to be big O of 1 plus n plus 1 plus n. You know, all together, you still get linear. Okay? Question? Yes, I'll take questions now before I move. J is less than n? Yes, because we are trying to say, after this point over here, we are trying to copy things over, right? No, not n plus 1. Because if you do n plus 1, it's going to go out of the bound of the array. How about we do an example here? Okay, yeah?
Like, I don't know if you're confused, but when you said j to I plus 1, so it's like pointing at 3 in this example.
Yeah.
But then you're assigning j plus 1 to aj, so you're skipping the third element.
J is I plus 1. Why don't we see? Okay, there could be a typo in the code. Why don't we try? Okay, let's try. It could be. Why don't we see? So now in this case, we know that J is going to be, J is actually I minus 1, right? Okay, I minus 1, so we should really get result. The first one we're going to get, result is, so that's going to be I plus 1 plus 1. Oh, I see, there's a typo there. Okay, so I should change that. Okay, very good. Okay. Yeah, thank you. I'll change the slides. But guys, hopefully you still get the idea. Somehow we want to copy Tom over here, Jin over here, and Simon over here. That's the point. But in the worst case, what if I is actually 0? In this case, you're really copying almost the entire array into the new array in the third stage. Okay, so you still get linear. You cannot get around with that. Okay. Okay, any more questions? Why? Oh, okay, over here. Think about this. Okay, I'm trying to think about the number of iterations I have for the third stage, right? Let's look at the bounds over here. You can see that J initially is I plus 1, okay? And J is less than n, which means the maximum value I'm going to have for J is going to be n minus 1, right? I'm just trying to calculate the number of iterations I will have. So basically, it's going to be from I plus 1 until n minus 1, the J's value, right? So if I want to see how many numbers are in between, so let's say you learned about the intervals maybe in your calculus class. If you got a closed interval, let's say from A to B, and how many integers do I have? It's going to be B minus A plus 1. That's what I did. Okay? Yeah?
Also, if it was just in j equals I, then the assignment part would be right, the shifting part.
Which one? Which?
Like instead of changing result if j minus 1 equals aj, you could also just change like if j equals I, then the shifting would be right.
Yeah, sure. Let's keep that version over there. Yeah. Mm-hmm. Guys, any more questions? If you still confused, go ahead. Huh? You want to repeat? Go ahead.
So you know how there is like an indexing error for the result j? Yeah. You could also, instead of changing it in the result j equals aj minus 1, you could just change.
Yeah, you can also, So either you keep the I plus 1 over here, and then over here you should say result j is assigned to a j minus 1. Okay, that's one way to do it. Or you can also say j is initialized to be just I. In that case, you can say j plus 1 and then j. So you just got two options there. Okay, yeah, either way will work. Okay, any more questions? But the main message from this example over here is, if you are trying to insert into an array, or let's try another one. If I say remove from a particular position from the array, in that case, you still have to shift everything to the left to actually fill that empty slot. In that case, that's also going to be linear. So whenever you want to change the contents of the array, if you want to insert something into it or remove something from there, it's going to be expensive. It's going to be linear. Okay? Those are the circumstances you should not use array. You should use something else. Okay? Any questions? Are we okay? Yes. That should be, no, it's only, yep, so we start from 0 and then until I minus 1. Yes, you got I iterations. Yeah, it's I versus I minus 1. You can drop the lower term as well, right? Yeah. Yeah. Yeah, okay. You know, sometimes I know, yeah. Yeah, maybe I'm not being precise enough. Yeah. And I can be very big, right? I can be almost as large as n. Yes. Good. Guys, any more questions? Okay, before I move on to linked list. Okay. Good. Okay. That's good. Okay, that'll be linear. That's a conclusion. Now, linked list. We'll only talk about a particular kind of linked list called singly linked list. There's another kind called doubly linked list, which we will not cover in this course. You will learn about that in 2011. Okay? But hopefully this one should give you sufficient ground. If you want to study by yourself, doubly linked list, you can feel free. Okay? There's not too much extension to it. Okay? But let's focus on this. Okay, we know that for array, it performs well in indexing, but poorly in inserting and deleting. So now we can now have a data structure. Again, remember what I said last time. There is not a data structure that's silver bullet, which means the linked list we're going to introduce to you right now is going to perform very well in inserting and deleting. But for indexing, it's going to perform poorly. Exactly the opposite to the array. Which means, well, because if linked list performs so well in both cases, we can completely abandon the array. But that's not the case. Okay? So whatever that array performs poorly, we can use linked list to complement that, and vice versa. Okay, that's my point. Yep. Okay, let's talk about linked list. Now, I want you to think back to an example we talk about when we talk about classes and objects. Remember the person class, we said you may have a spouse attribute over there. I will only say that in some way the singly linked list data structure is a little bit similar to the person with a spouse. Similar. Okay? I will let you draw the connection maybe after class, but just keep that in mind. Okay? So what is a linked list? It's also a linear sequence. When I say linear, it simply means for every element in your collection, you always have the sense about the next elements. For the array, what's going to be the next element to position 0, position 1? And what's going to be the next one for position 1, position 2? And now for linked list, we got a similar notion, the notion called next. If I go to a particular position in my linked list, I can always say, go to the next one, and then go to the next one, or go to the next one. It's completely linear. So what would be a nonlinear data structure? We'll talk about this maybe after reading week. Okay? So now let me give you some idea about linear versus nonlinear. Okay, so we talk about the difference between linear and nonlinear. So linear, so that would be, for example, array is one possibility of linear data structure. You got 0, 1, and 2. For example, what's the next one to 0? That'll be 1. What's the next one to position 1? Position 2. You got only a unique next elements, immediately next. The one we're going to introduce right now is called linked list. Conceptually, this is how you draw. I have the very first position over here. That one has a reference to the next objects. And then that one there has another next reference to the next objects. So now, and that one there may not have the next objects. I would just have to say now. That's a linked structure. Okay? So now let's say this is the beginning of my linear structure over here. How do I go to the end? I gotta start from the very first one, and then keep going to the next, keep going to the next, keep going to the next, until I reach a null reference for the next. You gotta keep going until you have nowhere, you cannot move any further, basically. That's very different from array, because for the array, you got fixed size. You always know what the last position is. But for the linked list we're gonna talk about, you have no idea, okay, in general, okay? Okay, what about nonlinear? In nonlinear, we're going to talk about something called binary tree. This is something called nonlinear. Okay, for example, tree. For example, you have maybe, it can be this, like that, that. That's a tree. That's nonlinear. Okay, we'll talk about this later. And also, something you will learn about in 2011, something the most general structure you may have is called graph. So this is tree, and otherwise called graph. You may have something like this. Maybe that. That's a graph. My point is they are not linear, okay? You'll learn about tree later in this course. You'll learn about graph in 2011, okay? Okay, let's go back to linked list. Okay, now the way we refer to each position in a linked list, we say something called node. I'll show you the code in just a moment. Let's go over some concept first. It's called node. So each node in the list, there are two attributes we're going to define. So one is called the elements of the node, okay? And the next one is called the next one, your neighbor. Let me draw some analogy here. If you think about this one here, singly linked, okay, singly linked list, the one that you cannot see. So basically, we got two things over here. Okay. So now let me draw that. So how does it look like? At the runtime, the object looks like this. I have something called node. I will define that in just a moment in Java. And there are only two attributes. One is called elements. The other one is called next. The element part, let's say string, just for the purpose of illustration. It can be maybe Alan. Let's say we have a link chain of names over here. So now what about the next? Next is going to be a reference to another node objects, just another one. And then for that node there, it also has two attributes. It has elements, let's say in this case, it's mark. And then you also have next. Let's say you only have a chain of two nodes. In that case, the next reference here is simply null. Means points to just nowhere. So we have a chain of two linked nodes. And let's observe several things from this simple example over here. So usually we only keep to say this is the very first one in our chain. We call it a head. We usually only keep that reference there. Let's start with that. Now, how can I get to the end of the chain? Can I go there directly? No. In array, you can. In array, I can simply say A and then square brackets a.length minus 1. That's easy. Just do simple calculation. But in this case, no. You got to do indirectly. You got to use a loop. I'm going to show you the loop in just a moment. I would say you have to say start with the head and keep following the next reference until the next reference becomes null. Now, and then you know you should stop. Basically, the node whose next reference is null is the last node in the chain. Okay? Okay, and then let's see this. Okay, that's just another example here. So now, again, you should really try to contrast in the linked node over here. The positions are relative. They are not absolute, right? So relative, which means I can always only go to my next neighbor, next neighbor, next neighbor. I cannot say, I'm here, but now I want to go directly to the maybe the second node in the list or 10th node in the list. Okay, I cannot say that. It's going to be expensive. Okay, now, this one's already, I have already answered that. What's so special about the last node in the list? Doesn't have the next. Yep, exactly. You can see that over here in the append node, you can see that over here, if I just want to draw another one, let's say another node over here. Let me erase this over here. If I just want to draw another node over here, let's say a third node, I have elements, I have next. Let's say this one here, Tom, over here. And let's say this is the next, the last one, just now. Okay, so now you can see that this is the last node. This is the last. If you compare this, the structure for the last node, together with everything else, over here, this is everything else. You can see the structure is a little bit different, right? Of course, every node has a name, has the next. But you can see, except for the last node, every node there has the next reference, not now, right? That's something I want to point out to you. Okay, they always point to the next. Okay. Okay, good. Okay, why don't we see some code over there? Okay, and then we'll see. Okay. How do you implement? Is a typo there. We are not using generics. Okay. How do we actually define link node in we got two classes to define. Let's go over the class definition there, and then we'll try to go through some developments. Okay. Okay, there are only two classes we got to define. The first one is called node. So node is a class over here, and then we got two attributes only. We got elements, we got next. So for simplicity, let's assume we only store strings in the list, in the linked list. And then you can see the next attribute over here, the type is just the same as the class name. It's recursive. We said that. Recursive means it might just point to itself, like a spouse, right? Spouse also has the same type person. Okay, let's see the methods we have. The methods we have are very easy. First of all, we got constructor. For the constructor here, you just pass a new name over here, and then you pass its neighbor. Okay, I will show you how you can define that in just a moment. And also, you have get element, getter, and setter, basically. Get elements, also get the next. Also, you can set the next, and also set the element. We got these setters and getters. Okay, so that's about the node class. We have just another class, which I will go in just a moment. Okay, but let's now see example right away. Okay. Now, you can see that code over there for the node. You see the diagram is really bad. Actually, it's not too bad. You can still see the critical part, right? Let's see, if you look at the top, let's say we want to create a chain of nodes like that. So the first node is going to be Alan, the second node is Mark, and the third node is Tom. Let's say that's something we want to create. Okay? And you can see for the node that contains Alan as the element, its next reference points to the node whose name is Mark. And that node, the next reference of that, is pointing to another node whose name is Tom. Right? That's not how the structure we like to create. But how do we do that? I'm going to show you both two different ways to do it. Okay? So now, first of all, you can see approach one over there. So by only 3 lines of code, we can do that. But we want to see why, right? Okay, let's see why. Okay, let's see how we can analyze this. So now, first of all, let's see what does it really mean when you say new node over here. Okay, you can see that. So let me call this step number 1. What does 1 do? So we are creating a new node objects, okay? So now let me put it here. We have a new node objects. Okay, number 1. So we have a node object here, and every node has an element, it has a next. Elements and next. And then you can see that the constructor over here, it takes a string, name, and also takes a reference to its neighbor. Now for this particular case, we have Tom and we have now. Okay? So that means element is going to be Tom. And its next reference is going to be now. So far so good? That's step number 1. That's only 1. And what about, let's call this part here 2. And this part over here is number 2. In that case, for number 2, we are basically saying Tom is going to point to this particular node. So Tom is a node. So Tom is a node where the element is the string Tom, and the next is simply null at the moment. So that's what step number 1 and 2 will do for you. Okay. Any questions so far? Just 1 and 2. Okay. So now the interesting bit is going to be the next line. Okay. What does the next line mean? And I just realized I should have drawn this to the rightmost position. Let me do that. Again, that's really the advantage of having an iPad. I'm going to do something very cool. What I would do is I'm going to select this and move that to here. Okay, good. Everything, oh, no. No, you see. Sorry, got to practice this. Oh, okay, one more time. Yeah, I could have redrawn, right? Yeah, you know, I'm just having fun. Okay, good. Okay, done. Okay, everything, all the explanations still apply. So now that's the node. Okay, let's see the second line. What does the second line do? Okay, now let's highlight that. I'm going to use a different color on my screen, so when you watch a recording, you can see. So let's see this particular one over here. What does this one do? Okay, yeah, there's no difference on your screen, but on my screen, it's a huge difference. Okay, so now let's use use different color here. Let's call this number 3. What does number 3 do? Again, we are creating a new node. Okay, number 3. We are creating a new node over here. New node, every node has the name, the elements and next. Element and next. Okay? So now we say that the name, the element is going to be Mark, right? So that means the name is going to be Mark. Now, what's really tricky is, what does it really mean when we pass Tom over here? Right? That's a tricky bit. What does it really mean? When we pass Tom, remember we talk about call by reference. Call by reference simply means when you pass an object as an argument, you only make a copy of the address of the object variable, right? So now, Tom is referring to this particular object over here, so we are copying its address and pass that to this method here, okay? And what does that method do? That method there is simply the constructor, and this is what it will do. You simply say, whatever object you're referring to right now, which is this node, its next is going to copy the address of the Tom objects. Okay? So what you will do is, it will simply do that. So the next is going to refer to wherever Tom is referring to, like that. Okay? Any questions until now? It's really important. Okay, go ahead. Yes, you mean in the argument there, right? Yes. Okay, yeah. So no, it doesn't create a new object. You can see you only create a new object when you have the new keyword, right? So you can see that for this particular step, you have new over here. So that's exactly the object I'm creating here, but it has nothing to do with Tom. Tom is some existing object variable, and Tom is basically this address over here. So Tom's already stored the address of this particular object. We're just making a copy of that. Remember, that's what call by reference means. Okay. Okay. So after this, we're gonna have again this particular part, which is number 4, and this part here, we're going to make Tom point to it. Oh, sorry, not Tom. Mark. Mark over here. Yeah. Alan will be the next step. Yeah. We're getting there. So now, so far, you can see we build backwards, right? Approach 2, I'm going to show you how you can build forwards. The reason that I show you both is you should know both. Okay? Guys, any question until now? It's really important to get the basics right because we got quite a number of methods for linked list. I will go through the very first few in very much detail with you. The rest is really up to you. Okay? Yeah, questions? Exactly. So that's why I got two different approaches. So the problem is really the same. I want to have this sequence here, Alan followed by Mark followed by Tom. One way to do it is building backwards. Another way is building forwards. Okay? Huh? Head. Don't worry about head. We'll talk about head in just a moment. Okay? We're just building a chain. Okay. Now, one more. Okay. So now the third line over there. Over there we have basically new node, Alan and Mark. Okay. So now let me call that. Maybe would that work? So this one, what about 5? That's bad. Okay. Okay, well, let me choose a different one. What about? Okay, I'll just. Okay, 5 over here. What does 5 do? Similar. We are creating a new node object over here, a new one. And then we have also this one has element, it has next. And what about for elements? It's going to be point to Alan. And then, again, call by reference. We're passing Mark over here. So that means when we are calling this constructor over here, we're going to say n over here, the parameter, is going to be a copy of Mark. Okay? Something like that. Now, if you put Mark there, that means n is going to point to wherever Mark is pointing to. So we're building backwards over here. Okay? And finally, this is number 6. And then we're going to assign Alan to it. So now let's play with the dot notation over here. What's Alan dot elements? Oh, let me say it again. So Alan is here. That's so we have 3 variables over here. We got Alan, we get Mark, we get Tom. Let me just mention the dot notation. Tell me what the value is. Okay. What is Alan dot elements? Alan, quote string. What's Alan dot next? It's the Mark objects, right? So now we have aliasing as well. You can see that. Let me just mention that. When you say Alan dot next, that's exactly equal reference comparison Mark. Exactly equal to that. Okay. What's Alan dot next dot name? Oh, sorry, no. Alan dot next dot element. Mark, quote. Okay, one more. How can I refer? Now, question for you. How many ways there are for me to refer to this string over here? How many ways are there? I heard 3. That's a good sign. 3, right? Let's go from the shortest one. I can either say Tom dot elements. I can say Mark dot next dot elements. I can also say Alan dot next dot elements. Okay, good. Hopefully you get an idea. Any question about approach 1? I would say approach 1 is slightly trickier than approach 2. You might prefer approach 2 actually. Okay, yeah.
We are basically assigning the answer next by hand.
Mm-hmm.
What happens if say Alan next equal to Mark and Mark next equal to Alan?
Alan dot next is assigned to Mark. I'm not too sure what you want to do. Okay, so can you say it again? What do you want to do? You want to say Alan dot? Oh, circular. I see what you mean. I would say for the purpose of this course, you don't have to worry about circular list. But I might, maybe, you know what? Let me leave the circular topic maybe to next week. I can maybe show you a method where you can determine if your list is actually circular. That's actually possible to do it. Okay, I'll talk about it. Okay, so what? Okay, so now let's go on. I'm not sure why my Apple Pen is failing on me. No, actually I charged that. I did charge that. Guys, can you bear with me for 30 seconds? It could be that I have to. Okay, what I should do is I gotta disconnect. I have to connected. Yeah, bear with me for just 30 seconds, okay, and then I'll come back. Okay. Okay. Oh, that's really bad, actually. Okay. Okay, it is connected. Okay. I'm not sure why Apple Pay is failing. What about this? Let me show some slides. How about that? Okay, I'll see what I can do. I will try to avoid writing on the chalk. That's really something I want to avoid. Sorry about that. Today I'm not sure what technology is failing on me today. Okay, so now we still got 10 minutes. Let's see how we can kill these 10 minutes. Okay. Okay, so now let's now see approach number 2. Okay, for approach number 2. Since you cannot see the iPad anymore, can we just see approach number 2 over here? Let's use your imagination. How about that? Okay. Huh? Yeah, you know what? Okay, you know what? I really don't like it. Okay, what about that? Okay. Okay, for approach number 2, okay? You know, my worry is because if I do approach number 2, you cannot see the recording. Actually, okay, anyway, we do the best we can. Now you can see it, but if you're watching recording, you gotta use your imagination, right? Yeah, exactly, that's good. Okay, what about approach 2? Let's try to do that for approach 2. The line number 1. What does line number 1 do? So when we say Alan is going to be a new node, Alan now, okay? So now this one is interesting. So we are creating not Tom first, we're creating Alan first. So what we have is a node over here. I gotta make sure I got the right sequence because I cannot just, okay, good. So node over here. So we have elements and we have next. In this case, Alan is going to be the elements. And the next is simply going to be now. Just that, okay? That's what line number 1 will do. What about line number 2? Similar. So basically, for approach 2, we are trying to create 3 independent nodes and then set the links in the last stage. Okay. What about for line number 2? So we have another node over here, and then we have elements and we have next. And in this case, it's going to be Mark. And this one, the next, is also set to now. Right? What about the third one? The third one over there, so we have also node over here. And then we have elements and we have next. And then we have Tom. And we also set the next to be now. So far, so good. We got 3 independent nodes. They have no connection between whatsoever. So now let's see line number 4. When we say Alan does set next, okay? Let's see what I can do. So let's review what set next is. So remember in the node class, so we have class and we have node. One of the mutator is void set next. And over there we have node, and over here. And it has only one single line, which is this dot next is assigned to n. That's what it has, right? And of course, we got the next attribute in the class. So let's try to see this. When we say Alan dot set next, so what does that mean? And we say Alan dot set next mark. So now you can see that this mark over here is going to be copy by reference, a copy of mark, which is this object over here, right? Oh, I forgot to point to them, okay? Alan here, and this is Mark, and this is Tom. So now Mark over here is going to be a copy of Mark. So it's going to be copied to here. So I can say this is going to be a copy of Mark. And it's going to be a copy of Mark. And you can see this is the current objects. That's this. So this is going to be replaced by Alan. So what do? We say Alan.next is assigned to Mark, which means copy the address of Mark and store that in Alan.next. Copy the address of this object over here and store that into Alan.next, which means it's not going to point to null anymore. It's going to point to this object here. So we are setting forwards. Yes, questions?
Why you just don't put like instead of none mark, like adding mark and
Very good question. So the question was, can I say something like this? It was a fantastic question. Let me put it here. The question was, can we simply do the following? Alan is new node over here. And then we say Alan here. And then Mark. I think that's what you meant, right? Okay, good question. And then we say node, Mark, over here is new. Let me just complete that for completeness. New, and then we have Mark over here. And then we have Tom. Okay, keep this in mind. Don't do this in lab test 3. Because the code would not even compile. Why? Well, you talk about Mark. Was Mark even declared? No. Mark is declared exactly the next line. Otherwise, of course, I wouldn't really, just do another extra 2 lines. I had no choice.
Can we do object exceptions like node Alan, new node Alan, new node Mark?
Don't do that. Yeah, don't do that. Okay, but you see the point, right? That would not even compile, right? Okay, guys, do you see that? Do you see why it doesn't compile? You have to declare something before you can use it. Mark was declared after it was used. Okay, so you cannot, so that would not even compile. Okay, so this, so far we have done Alan.setNext Mark. Let's do the final one. We do Mark.setNext. And then we have Tom. Okay, it's going to be similar. We're calling the same method here, but now n is going to be just Tom. And it's going to be Tom over here. And the current object, this, is going to be Alan. Mark. So we got Mark.next is assigned to Tom, right? So now Mark.next is assigned to Tom. So that means it's going to point to this object here. Okay, any questions? I'm not sure which one you prefer, but both approaches work. You can choose whichever way you like. But maybe approach 2, even though it takes 2 more lines, but maybe it's easier to keep track of. But for approach 1, you have to know exactly the order, right? You got to build backwards. Okay, doesn't matter which one you choose. Okay, let's go a little bit further. Okay, let's now, since we already got this chain structure over here, let's just trace one method, and I'll continue the rest. Okay. Now, let's say, in this way, how do you count the number of nodes in the chain? How do you count that? Okay. Apparently, you can see that the answer should be 3, right? It should be 3, but the chain can be arbitrarily long. We simply don't know where the end is. In this case, that should be the end. Okay. How should we do that? We can use a while loop, for example, right? until the next is not null, exactly. But now we got to do this mechanically, right? We're going to do this in a Java code, okay? So let me talk about the idea. You can certainly follow the code over here. The code is not very long, only that. But let me try to give you some intuition, like how you can do that. The main thing is here. If you see line number 2 and 3, so there are two attributes here you got to keep in mind, okay? I'm going to put it here. So there are two separate attributes. One is called size, integer size. And the second one is another node. So this is a tricky part. But you will see this pattern here always. So make sure you learn this well. Current, I say that is equal to head. Let me just replace the head, just for this example here, okay? I'll just say it's simply going to be the first one, just Alan. Okay? So now what does that mean? I'm just creating another variable, but I'm not really wasting too much space because that's just a copy of the address, right? Copy the address of Alan and store that into current. So what does that mean? That means I have another pointer pointing to this object here. It is called current. And this current has a special name, which you will learn quite a lot in 2031. It's called a cursor. Cursor simply means it's going to point to element one at a time. And somehow, we're going to move the cursor from left to right. Every time when we move from left to right, we're going to increment the size counter. Initially, it's simply just 0. If we are able to move from here to here, increment by 1. From here to here, increment by 1. From here to here, and no further, increment just last one. So you get 3. So that's the intuition. Okay? Doesn't sound too bad, right? Maybe? Okay. Let's now see a critical line of the code inside. I want to, okay, can we just look at line number 6? Let's try to understand what this is doing. Current is assigned to current.getNext. What does that mean? Let's try to understand this line. That's the most critical line. When I say current is assigned to current dot get next. Let's just try to understand this line here. What does that mean? So it's just an assignment. We're going to assign current.getNext, which is some object variable, some object address. Current.next, whatever address it is, store that into current. Okay, let's think about how this works first, and then we can see how to draw the diagram. What currently current is pointing to this object here. What's current.getNext? Current.getNext store the address of this object over here, right? Which is just mark. In that case, we store the address over here into current, replacing itself, basically. Now, what will current be? Well, current is as if we move the cursor over here to the right by 1 position. Okay? It's as if we do that. And we keep doing this in the loop. You can see line number 5 and 6, they are part of the loop body over there. And we keep doing this until the current becomes null. You can see we stay in the loop. In line number 4, we say we stay in the loop as long as current is not equal to null. So what does it mean when we exit from the loop? That means current becomes null. In which case, we simply exit from the loop and we're done. So keep moving current from left to right, and until if current.next is null, then we stop. That means we can stop counting. Questions? Yes.
The get next method, is it like a standard method?
Yes, it's a getter. It's a getter for. So for example, here, see this is a set next to the setter, right? So you just got another one called getter. You can see the slides. We got the code over there. Yeah. Okay, any questions? So this is what I would suggest to you to make your Tuesday much better. So on Tuesday, I have to show you all the methods for simply linked lists. Go over this very, very carefully and see how you can understand the code before. And then on Tuesday, we'll finish this topic.